All right, hopefully you guys can still hear me. I apologize for glitch in the middle. I'm tired of starting over and trying to do this from the beginning. So we're going to pick up where we were, and hopefully that's going to be okay. We were talking about the common ion effect, and we were talking about the fact that we had the presence of fluorine from the sodium fluoride, and that affects what we're looking at for this. Now let's go ahead and keep talking about what it is that we've got going on here. So let's talk about the effect of acetate on the acetate acetic acid equilibrium. Helps if I share my screen, huh? So like I said, we were talking about the common ion effect, the fact that we had F minus that was present from the NaF. That's what we're looking at there. Now let's keep going and see what else we can talk about. Here, we're going to be talking about the effect of acetate on the acetic acid equilibrium. So acetic acid is a weak acid. It's CH3COOH. That can dissociate to become H plus CH3COO minus. Now remember, technically, from a technical standpoint, this doesn't happen like this. So what actually happens in solution is that we have CH3COOH plus H2O goes to H3O plus the CH3COO minus. And of course that doesn't fit very well, but there are a couple of things that you'll notice when we do that. If I were to use this as my K, the water would not appear because it's a pure liquid, so that would not appear there. And we'd end up with the H3O plus, so we then end up with our Ka equal to the H3O plus times the CH3COO minus divided by the CH3COOH, which looks shockingly like what we talk about when we leave out the water. The only difference is that we talk about it in terms of H plus instead of H3O plus, okay? We are lazy chemists. That's why we do it as just H plus. But understand, H plus does not actually exist. It's always the H3O plus, and that's what Alex is going to be looking for. I really don't care which one you give me. It is not important to me. We don't, I mean, I tend to leave the water off because it doesn't appear in there, and because since it doesn't appear, it complicates the issue. All right, anyway. So if that's the equilibrium that we're talking about for CH3COOH going to H plus CH3COO minus, and then we add sodium acetate to that same solution, sodium acetate is a strong electrolyte. All of our sodium acetate becomes Na plus and CH3COO minus. So that increases the CH3COO minus concentration. So if I'm looking at an ice table, CH3COOH going to H plus CH3COO minus. And we have an initial concentration here, something that's not zero. That means that this equilibrium is going to have to shift this direction. Okay, because I have the presence of the CH3COO minus already, I have to shift. And that's what we're talking about when we do this. Now, that is exactly what we've been talking about with Le Chatelier's principle. So we know we're going to have to go backwards. And that means that my pH is not going to be as low as it would be, i.e. my H plus concentration will be less because I cannot dissolve as much of that acid in the presence of the CH3COO minus. Okay, so that's what we're talking about with that. Remember that we have to look at all of these factors. So that's part of what we need to be able to talk about, okay? So here's an acid-base example, similar to what we've talked about before, but now we're looking at an acid-base example of our common ion effect. And we want to know what's the pH of a solution made by adding 3 moles of acetic acid and 3 moles of sodium acetate to enough water to make 1 liter of solution. So again, we're looking at a similar situation to this right here. We're talking about acetic acid, and I have 0.30 molar because there's 1 liter, so it's 0.30 molar. Okay, and of course, this is also, if I can erase that, 0.30 molar. Okay, we know that this is supposed to be coming apart. We want to look at the effect that this has on its ability to do so. So that's why my change is going to be minus x there. I'm going to get a plus x on that and a plus x on that. And I want to determine what those equilibrium concentrations are going to be. In order for me to do that, I have to set up my Ka, which has this form right here. And of course, my Ka value is 1.8 times 10 to the minus fifth. I've had some people ask me, where am I pulling these random values from? There is a, on the handouts that you guys get, and let me pull those handouts because I am that neurotic. Where did I put them? I don't remember where I put them. Sorry, I don't remember where I put them. So anyway, but in those handouts, there are tables of Ka and Kb. So they were not initially present. What had happened is that they were actually appearing underneath one of the other tables. And so you couldn't see them, but they were there. Doesn't mean anything to you guys because you couldn't see them, but that's where they're from. So there are a couple of places that you may find K values that you need on the test. Look through all of your end materials. It may be somewhere in there, even if it's not in the table that you expect it to be in. It also might be somewhere else on the test. So I may ask you about a system that I already talked about. So if I talk about it in one place and I give you the K there, I'm not going to repeat that. So you may have to look at other parts of the test to see if it's in there as well. Okay, so my Ka is 1.8 times 10 to the minus fifth. That's equal to the expression that I had before. I know that in this particular case, we want to be looking at our x times that 0.30 molar over our 0.30 molar. And again, that's assuming that the x value is going to be small compared to the 0.3. That's a fairly reasonable assumption. I can almost guarantee it. That means that this is going to drop out, and 1.8 times 10 to the minus fifth is going to be my x value, which of course is way less than 5% of 0.3. Okay, so that's what we're looking at there. Now, remember the Henderson-Hasselbalch equation. So Henderson-Hasselbalch says pH equals the pKa plus the log of the concentration of the base, which is the CH3COO minus, over the acid, CH3COOH. If we were to look at that in this case, we'd be looking at pH equals the negative log of 1.8 times 10 to the minus fifth plus the log of 0.30 molar over 0.30 molar. That then disappears. This whole term disappears. And my pH is equal to the negative log of the Ka value. That's an optimum buffer. Since I have the same amount of the acid as I do the anion, that means it's an optimum buffer. And so my pH equals my pKa. All right. One of the things that you need to understand is no matter how I do this, through Ka or through the Henderson-Hasselbalch equation, you should get the same answer. Because the Henderson-Hasselbalch equation is just taking the negative log of every term in my Ka. That's all it is, and then rearranging a few things. So we should get the same answer from both of them. Shouldn't matter how you set that up. As long as you have your concentrations what they should be, then we shouldn't need to worry about which way we do that, okay? So I can see that my pH is equal to the negative log of the H plus, which is 4.74. That's the same result we got before when we used the Henderson-Hasselbalch equation in lecture 3. pH equals pKa of this thing, which is 4.74. Okay, that's what I was just talking about. All right, so that's our acid-base example. So common ion, we have to, again, consider how much of this material do we have for this anion, how much of this material do I have for the acid, and then what is the effect of the other ion in this solution, which here is the H+. Okay, it's no different than what we talked about before, except in this case, we're talking about pH. Okay, so that's that. Now, questions, comments, problems? Hopefully not, but if there are, I know that you know what to do. Go ahead and reach out to me. I will be happy to try and answer those questions if you have them. Now, I'm going to get myself a new piece of paper because we're moving into something else, which is talking about complex ion formation. Now, I did use this particular table to do a couple of other things in the homework. So there are some values off of this that I used in the practice problems. Since I had given this to you previously, I figured there was no problem with doing that. This is also available in your textbook. So there is a value that comes from, that you can get from there as well. Since there is no table of these complex ion Ks on the test, I would have to give you one if I wanted you to use it. All right, that's as much a reminder for me as it is information for you. What we're looking at with complex ion formations is that metal ions can act as Lewis acids. So they are electron pair acceptors. If they're electron pair acceptors, they can form complex ions with Lewis bases. And our most famous Lewis base is NH3. So it's got a lone pair of electrons, so they can donate to that cation. Cn- is another good one. We've got a couple of them that appear in here. Actually, OH can act in the same way. So you'll see that there are a number of them in here. And what happens when we have a solid or a cation that's not particularly soluble, if it makes a complex with one of these things, that solubility goes up a lot. You may be able to see that these values are, big, 10 to the 7th, 10 to the 21st, 10 to the 13th. Those are really big values. So how is that going to change the situations that I'm looking at? How does that affect my solubility? Well, let's talk about that, because that is going to be something we have to consider. Let's go ahead and move on to our next slide. How complex ion formation affects solubility. So what we're looking at here, and let's see if I can get this zoomed in a little bit. So I have AgCl. NH3 reacts with the Ag+, and that forms this AgNH3 2+. Okay. And the reaction with NH3 reduces the concentration of free Ag+, and that drives that reaction forward. Okay, so we get more solubility of the AgCl because I've effectively removed one of those products from that reaction. Same exact thing. It's now going on to react to use something else, and therefore I can get more of the Cl- into solution. Okay, I'm going to zoom back out so that hopefully we'll be able to see things. So silver chloride is insoluble, has a KSP of 1.6 times 10 to the minus 10. In the presence of NH3, solubility will greatly increase because Ag+ forms that ion, and therefore the Cl- is more soluble. This shifts the dissolution equilibrium of AgCl forward since we remove the Ag. Okay, I said all of those happy, lovely words. Hopefully we understand the happy, lovely words. What does it look like when we actually do calculations? So we want to calculate the molar solubility of AgCl, given that the KSP of AgCl is 1.6 times 10 to the minus 10. We can do that without any other species present, and we set that up as AgCl being a solid goes to Ag+, which is aqueous, plus the Cl-, which is aqueous. And again, if I set this up as a rice table or ice table, depending on if you leave that there, I don't care about the AgCl because it's a solid. I initially have none of the Ag or the Cl. That means that my change, this is going to be a plus, this is going to get plus X, and they're both 1. So there we go. My equilibrium I haven't solved for yet. But that means that my KSP, which is 1.60 times 10 to the minus 10th, is equal to X squared. We take the square root of both sides, and that gives you an X value of 1.26 times 10 to the minus 5th. Okay, And it is 3 sig figs because I started with a 1.60 being 3 sig figs. So our answer should be 3 sig figs as well. So that's the solubility that I'm looking at when there's nothing interesting or weird or different going on. Okay. Now we want to know what happens. What if I add a 1 molar NH3 to this solution? Well, what happens is that we go through the same process. We have this same reaction here, but then the Ag plus, which is aqueous, can react with 2 NH3s to give me Ag NH3 2 plus, okay? And that has a K of its own. So the K expression for that is, of course, my product, Ag NH2, sorry, NH3 2 plus, I apologize, over the Ag plus and the NH3. Okay, we're assuming that this is not being done in NH3, so we have a fixed amount of NH3 that we've added. So NH3 is not a pure liquid in this case. So that's going to be equal to the value that I've got, 1.50 times 10 to the 7th. And again, it says I took that from table 16.4 in your text. So I gave it to you here. It came from that table. That's where it's from. Now my overall reaction, all right, my overall equation is going to be the sum of those two parts, AgCl plus 2NH3